Okay, so we are going to talk about the most popular algorithm to solve linear programming in this lecture. But in order to do that, we need some of the concepts we taught in the previous lecture in the polyhedral theory. Because it's a Zoom lecture, I think just to remind people of the main concept in polyhedral theory. What is the most important conclusion we got from the previous lecture? That is, for any bounded linear programming problem, the optimal solution can always be obtained at an extreme point, right? That's probably the most important conclusion we get. And why that is true? Because of the Minkowski-Weld theorem, right? Any polyhedral can be expressed as the convex Hall of the extreme points plus the conic Hall of the extreme rays. I would argue is the most important theorem you should remember in linear programming. Okay, so having said that, an algorithm to solve linear programming can be thought about as finding the extreme point that give you the lowest, let's say you are minimizing, that will be the lowest cost of this linear programming, right? And just to refresh your memories, how do we actually define an extreme point, right? As engineers, we are interested in calculating extreme points, right? So the way to get an extreme point is for any linear programming problem, let's just find n linearly independent constraints and make them active, right? So if you have n linearly independent constraints, then according to what you have studied in linear algebra, the solution is unique. You have an n by n square matrix, an inverse exists. You can take the inverse of that matrix to find the extreme point. Okay, so that's last lecture. A little bit history about linear programming. It was developed, now it's over 70 years ago, right? Developed by George Danzig. He was treated as the father of the Simplex algorithm in linear programming, probably one of the greatest optimizers there. And the idea of the Simplex algorithm is very intuitive. Since we know the optimal solution will be at an extreme point, then the idea is just, let's say, we can iterate over the extreme points of a polyhedral until we find the optimal extreme points. Okay. So in this lecture, we are going to talk about how to do that. Okay. So here's a review from polyhedral theory, right? So we know that an extreme point is equivalent to a basic feasible solution, right? That's one of the important theorems which we didn't prove in class, but that's one of the important results you can remember if you are not interested in the proof, is that an extreme point is equivalent to a vertex equivalent to a basic feasible solution, right? So those three concepts are equivalent. And how to find a basic feasible solution, we first need to define what a basic solution is, right? In a basic solution, all the equality constraints are active, right? In linear programming, there might be a bunch of linear equality constraints, right? All those are active, and out of the constraints that are active at this point x star, there are n of them that are linearly independent, right? So n linearly independent equality constraints uniquely define a point, right? The solution is unique for n linearly independent equalities. And if beyond that x star also satisfy all of the constraints, then it is called a basic feasible solution, right? Just to remind you what we covered in the previous lecture. Any clarification questions here before we move on? Okay. So now let's think about what is a basic feasible solution for the standard form polyhedral, because the Simplex algorithm is built on the standard form polyhedral, right? So before we prove the theorem, let's think about how do we apply the definition of basic feasible solution to the standard form polyhedral, right? So it don't look like the theorem at this point here, right? So in a standard form polyhedral, you have linear equality constraints, AX equals to B, right? So A is a m by n matrix. And typically, we have m strictly, it should be strictly less than n. Okay, and all the rows of A are linearly independent, right? Why do we need m strictly less than equal to n? Strictly less than n. Right? Any quick answer?
So there's some degree of freedom.
Yeah, so there are some degrees of freedom, right? Otherwise, you have a unique solution or you have an infeasible system, okay? Just to refresh your memory, okay? And then besides this linear equality constraint, we have some linear inequality constraint x greater than or equal to 0, right? So since m is less than n, the equality alone will not define a basic feasible solution. Remember, a basic feasible solution means there are n of the constraints that are active, right? So besides these m constraints, m equality constraints, I probably need to pick, intuitively, you need to pick another n minus m x greater than or equal to constraints and force them to be 0 in order to get a basic feasible solution, right? So in total, you need to have n active constraints. There are already m of those, right? These equality constraints must hold, and then you need to pick a subset of those x greater than or equal to 0, right? Since you already have m of those, then you need to pick n minus m of those xi's and set them to 0 in order to get a basic feasible solution, right? Okay. Now the rationale is clear on this part, hopefully. Then the theorem is saying something slightly different, okay? So this is one of the definition of a basic feasible solution, right? You have the inequality holds, right? So those are n minus m of those constraints, and also you need to pick n minus m of those xi's and set them to 0. Now you have n constraints. This is one definition of a basic feasible solution in the standard form. Then the theorem is saying something different. It says, let's say you have a standard form, and then A has linearly independent rows. Then a vector x is a basic feasible solution if and only if we have ax equals to b. Of course, this has to hold true, right? We already have this part here as well. And then there exist indices of b. Let's say you pick some indices of b, pick m of those. We say the columns of those indices are linearly independent, right? So remember, A is a matrix, m by n matrix, and then m is strictly less than or equal to n, right? So in other words, if you look at the shape of A, it's like in this shape, right? Where m is the rows, n are the column, right? M is less than or equal to n. So A is kind of in this flat shape, right? So what this theorem says is we can always pick some columns of A, m of those. They are linearly independent. And if the columns were not picked, then we have to set xi equal to 0, right? It's an equivalent statement to the basic feasible solution we stated here, right? So why this is the case? Maybe first I'll let people absorb the statement a little bit, right? Any questions regarding let's say, the theorem itself before we show why the theorem is true? Yes?
Isn't this like a restatement of a theorem that we discussed last lecture?
Which one?
There was one where you said that if it was in a standard form, you have to do very similar procedure. Yeah, so the thing we talked about last lecture should be this part. I don't recall we have talked about this yet. So this is more like if you have a basic feasible solution, you should pick a subset of those columns, right?
So let's say you pick this, and that column. In total, you should pick m of those columns, right? And you form a m by m square matrix, right? So that matrix is non-singular, right? It's kind of what this theorem says. And if the column, for the columns that are not picked by those arrows, then you set those xi equal to 0, right? So in order to show this, show these two statements are equivalent, it's just a linear algebra thing, right? I'm not going into too much details of how to prove this. You can show this, let's say, first of all, we have a proof scratch. It's not a completely rigorous proof. To show that, let's say, first of all, to check the sufficiency, if A, B are satisfied, then clearly they are n-linearly independent active constraints, right? And then because those columns are linearly independent, you already have another n minus m constraints, then that is a basic feasible solution. And then for a basic feasible solution, there must exist at least n minus m active constraints. Together with ax equal to b, they form n linearly independent constraints. Right? In other words, if you are going to pick n linearly independent constraints, you can write those active constraint matrix in this form. Okay, so the B are the columns you pick from the A matrix, and this identity matrix corresponds to the xi's you set to 0. Okay, so in other words, the constraints we picked would be two parts, right? So the first part of the constraint is ax equals to b. And the second part of the constraint is sum of the xi's set to 0 for I in the set n. Those are the so-called non-basic variables, right? And if you look at the two parts of the constraints, they can be written in this form. Okay, so for example, let's pick all those xi's that we set to 0, right? This part of the constraints correspond to our identity matrix, right? Because those are xi equal to 0. And then we can divide this matrix A into two parts. The first part we call it B. The second part we call it n. Right? So the n correspond to the columns for this part of the constraints that hold xi equal to 0. Okay. So in other words, you can divide this m by n matrix into two parts. One is B, the other part is n. The B is an m by m matrix, and n is a m by n minus m matrix. Okay. Yeah, then that characterizes a basic feasible solution. Yes?
So that matrix that's formed, would it be a square matrix?
Yeah, the B is a square matrix, right? It's an m by m matrix. Yeah, and then that B matrix has to be non-singular, in other words, right? These columns are linearly independent. Okay. Other questions? I see some people are confused. So if you cannot absorb this right now, think about in an even simpler way, right? You have n variables, m of those has to be, okay, yeah, so let's say you have n variables, n minus m of those variables has to be 0, right? And the rest of those you can calculate using the linear equations, right? Okay, so if you are confused about the previous slide, it's okay. You can still follow what I'm going to talk about next, okay? So let's say we just define it this way. If X is a basic solution, then we call those variables xb1 all the way to xbm basic variables. and the remaining variables are called non-basic variables. Yes?
So here M is the rank of A, right?
Yeah, M is the rank of A. You have M linear equality constraints. Okay, so you can think about the B1 all the way to Bm are the indices of the variables you pick among the n variables. Okay. And then the remaining variable are called non-basic variables, and then those columns A sub B1, A sub Bm are called the basic columns, and they are linearly independent. Yes?
Are non-basic variables then just equal to 0?
Yeah, exactly. Okay. So another very simple way to put it, if you don't follow this, let's say a simpler way to put it. How to find a basic feasible solution of a standard form problem. So step 1, let's pick n minus m variable, n minus 1 variables, xi, let's say I in this set n, set them to 0. Okay, so that's part 1. You just pick a subset of the variables, set them to 0. Now you enforce n minus 1, n minus m constraints already, right? And second step is we need to enforce ax equals to b, right? So those are m constraints, right? The original constraints are m constraints. And now in total, you have n linearly independent constraints. Okay, that's a simpler way to put it. If you don't really want to read that theorem and so forth, you just believe what I told you is true. Okay. Yeah. Okay. So hopefully everyone understand this part, right? Fix some of the variable to 0, and of course you need to satisfy the original linear equality constraints. Okay. That characterize a basic solution. And those variables you fix as 0 are called the non-basic variables. The rest of the variables are called basic variables. Okay? Yeah, and then you can define something called the basis matrix, right? And those basis matrix are formed just by arranging the m basic columns next to each other. Okay? And the basic variables are vector xb. So xb is a subset of the variable which we did not intentionally fix them as 0. Right? Okay. And the xn variables are the, this xn variable, you can treat them as dimension n minus 1 m. The non-basic variables are the variables you fix as 0, and the xb are, you did not intentionally fix them as 0. Okay. And then the B matrix, as we talked before, it's a square m by m matrix, right? And then it's indexed by, let's call it, the first column is AB1, AB2, and all the way to ABM. Okay. Then you can write the entire variables x as a concatenation of the basic variables and the non-basic variables, right? And similarly, you can write matrix B as you put all the columns corresponding to the basic variable together, and this n matrix is all the columns corresponding to the non-basic variables. We can write this in a matrix form. And once you pick what are the non-basic variables, the basic variables are determined uniquely. Right? Because the B matrix is a square m by m matrix, right? And then because you fix all the non-basic variables to 0, right? So if you write this constraint, ax equals to b, again, we are going to break the A matrix into a square matrix B, and some columns corresponding to the non-basic variables, right? And then let's just write the variables here. Those are the basic ones. Those are the non-basic ones. It has to be equal to B, right? And let's just write it out. Then this equation is equivalent to B times xB plus n times xn equals to B, right? Since the non-basic variables have been set to 0, right? We already set them to 0, then this is equivalent to bxb equals to B, right? And in order to get xb, you just take the inverse of the matrix B. Yes?
Would the dimension of the the non-basic matrix still be m cross n?
Yeah, so it's a non-basic matrix is this n matrix here is not, right? So the n matrix is of R m times n minus m, right? So in total, A has n columns, right? The basic matrix take m columns, and then the non-basic one take the rest n minus m.
Okay.
Okay, yeah. Is this part clear? You just divide the variables into two parts, right? One part is the non-basic one, the other part is the basic one. After you determine the non-basic one, you fix them as 0, then the basic variable will be uniquely defined because B is a square matrix. Okay? Yeah. So now we are going to define something called physics direction, right? The reason we want to define this is because once I give you a basic feasible solution, how do you check if it's optimal or not? Right? That's the next question we are going to answer. Because we already know the optimal solution can be obtained at one of the basic feasible solutions. Right? Now, in order to build an algorithm, you need to know when the algorithm should stop. Right? I give you a basic feasible solution. How do you check if it is already optimal, or should I keep searching? Right. So, and that's the next thing we will gradually build up. Okay. So in order to derive the optimal condition, we need to define something called feasible direction. What it says is if X is an element of this polyhedral P, a vector is said to be a feasible direction at X if there exists a positive scalar theta for which X plus theta d is still in the polyhedral P, right? In words, it's like, let's say we are standing at a point X, right? I give you a vector d. Now you are wondering, can I go along this vector d and still remain feasible, right? So if theta is strictly greater than 0, then you can argue that you go slightly along the direction d, you still remain in that polyhedral set, right? That's why it is called a feasible direction. If theta can only be 0, then that is not a feasible direction, right? Meaning that you can only stay at the current point, okay? Yeah, so now we are going to define something called basic direction. Okay, maybe this is too overwhelming. Let me write it down gradually, okay? So that not to confuse you guys. Yeah, so now let's say we stay at a basic feasible solution. Remember, at a basic feasible solution, xb is b inverse b, right? That's what we just talked about. Then xn is the non-basic variables which are 0, right? Okay, so a basic direction means, let's say we pick a new vector, right? And then we select one of the non-basic variables. So now all the non-basic variables are at 0, right? What if we pick one of those and then change it to 1? Okay, so this is like, now all the non-basic variables are 0, and then we want to perturb this a little bit, right? Why do we want to change it to 1 instead of -1? Is because all the x variables has to be greater than or equal to 0, right? Yeah. So let's say we pick a j. Pick an index j in non-basic variable. Right? Let's just pick one of those. And then let's set dj equal to 1 and set dj, so let's use a different index. And all the others still remain at 0 for all I that is I in non-basic variables and I that is not j. Okay. Hopefully the notation is clear here. So in words, now all the non-basic variables are 0. Let's just pick one of the non-basic variables and change it to 1. But all the other non-basic variable will not be changed, right? We still keep it at 0. Right? That's a direction we are going to search to see if that's feasible. Does that make sense? Okay, so that's a direction we are going to search for the non-basic variable, right? But we haven't talked about how the basic variable will change. Okay, so now the question is, what about the basic variables, right? Okay. So for the basic variables, we can derive how they are going to change if we are going to change one of the non-basic variable to 1. So first of all, observe that the x is an element in the polyhedral, right? So x must satisfy ax equals to b, right? And when we are going to find the direction d and change the solution to x plus b, right? So now we already know that dj is equal to 1 and di equal to 0 for all the non-basic variables such that it's not j, right? Okay, so that's the direction we want to search, right? Then as you can imagine, now we do not have degrees of freedom anymore because once you specify the non-basic direction, the basic direction will be determined, right? Because we have we still have m linear equality constraints, right? So let's calculate how the basic direction would be. So first of all, observe that if we want to search and remain feasible, we need to have a x plus d equals to b, right? We still need to satisfy the linear equality constraint. So if you combine these two, that means the direction has to satisfy ad equals to 0, right? That's just a very simple thing. And then if you expand this, that would be, again, A can be divided into two parts, right? The basic matrix part and the non-basic part. And D can be divided into two parts, the basic part and then the non-basic part, okay? And then that has to be equal to 0, right? That's just rewriting the constraint. Okay, and then you just need to do the algebra. That's just b times db plus aj. Why that is the case? Because all the dn's, all the non-basic directions are 0. We already studied here, right? All the non-basic directions are 0 except the jth one, right? So the n times the dn would only be the jth column of n, right? because all the others are 0. So essentially, you can get this part. This equal to 0. And now, since B is a square matrix, then we got the direction for the basic variable is minus B inverse times the AJ. Okay, this is just doing some matrix multiplication here. Any questions here? Okay, so if you buy this, then this is a summary of what we did. If you want to change one of the non-basic variable to 1, all the other remain at 0, then we have to change the basic variable to minus B inverse AJ. And then this is called the jth basic direction, right? So if you don't really want to know the derivation, just believe me, this result is true. If you want to search over, go around the jth non-basic direction, this is a direction that is a direction to keep the linear equality feasible. Okay. Yeah. So the next question is that when is a basic direction a feasible direction? Remember the definition, if we go back, the definition of the basic direction is that there must exist a positive scalar such that x plus theta d is still in P, right? The key point is that the theta has to be a positive number. Theta cannot be 0, right? So when we are deriving the basic direction, we've only made sure that this linear equality constraint is satisfied. But we haven't made sure that if we go around that direction, all the inequality constraints are satisfied, right? Does that make sense? So let's check, right? So if you go along this direction D, right? Of course, we already made sure the linear equality constraints are satisfied. But the other thing we have to make sure is x plus theta times the d is still greater than 0, right? That's the linear inequality constraint. We have to make sure it's satisfied. Okay. So now let's check the linear inequality constraint. There are two cases that can occur. First is if x is a non-degenerate basic solution. That means if all the basic variables are strictly greater than 0, then it follows that there can always exist a positive theta such that the basic variable still satisfy greater than or equal to 0. Okay, so no matter what this dB vector is, if the xb is strictly greater than 0, as you can imagine, you can always find a small enough theta such that the basic variable are still greater than or equal to 0, right? And the non-basic variables are always feasible. Why? Are always greater than or equal to 0. Why is that the case? Because that's by construction, right? We just pick one of them to be 1, all the others are 0, right? They still remain non-negative. But then when x is degenerate, then D is not always a feasible direction, right? Imagine some of these xb are equal to 0, and the dB happens to be negative, right? Then you cannot really go along that direction. Okay, so we are not going to talk about non-degeneracy in detail in degeneracy in detail in this class. We just assume all the problems are non-degenerate. Yes.
I'm sorry, what is meant by x is degenerate? Is that just
oh yeah. So to remind you the definition of degeneracy. Okay. So degeneracy means at a basic, let's say at a basic feasible solution, more than n constraints are active. Okay. So an interpretation for this problem would be, we already pick n minus m non-basic variable, force them to 0, right? And then we have m equality constraints, right? So if some of the basic variables are also 0, then you have additional constraints that are active besides the n constraints, besides those n constraints you have picked. Then this problem is degenerate. Does that make sense? No? Okay, yeah, so let me rephrase that. So you pick the variables in set, let's see. So the variables in set n are the non-basic variables. They are n minus m of those, right? And you set xi equal to 0 for all the I in the non-basic set, right? And you have this constraint ax equal to b. Those are m constraints, right? So in total, they are n constraints, right? But if some of the variables, let's say there exist xi such that I is in the basic variables, but xi is also 0, okay? Then you have more than n constraints that are active here, okay? That is the case, because initially you pick all those in n to be 0, but if some of those variables that are not in n still equal to 0, then in total you have more than n active constraint, because you add them up, there are more than n of them, right? So if the problem is non-degenerate, then you must have xi, if it's non-degenerate, right? So xi has to be strictly greater than 0 for all the I in the basic index, right? Okay, that's why we say when it is non-degenerate, the xb has to be strictly greater than 0, okay? Yeah. So we are not going to deal with degeneracy, because if we want to deal with degeneracy, we will need to have 2 or 3 more lectures. Yes?
Can't you get a problem without degeneracy from a problem with degeneracy? So if you have your defining equation, or for the problem is ax equals b, can't you perturb a or b by an arbitrarily small amount to get a problem without degeneracy from a problem with degeneracy?
Oh, that's amazing. You are claiming a theorem in the textbook. Yeah, yeah, so there's you can check the reference we have. There is I think there is a homework, not our homework problem, but the problem in that textbook. You can prove that you can perturb those constraints by an arbitrary small number to remove degeneracy. Yeah.
Okay.
That's amazing. You already know that is true.
I mean, I just kind of guessed it because through the picture from last time.
Yeah,
but anyway,
yeah, exactly. Yeah, but what you said is a theorem. Yeah.
So basically, all the degenerate problems form these teeny tiny little holes that you can just very easily avoid.
Yeah, exactly. Yeah, you can try to prove that if you wish. Yeah, that is something has been proved already. Okay, other questions for this part? Yeah. So now I'm going to cover a very useful concept in linear programming. Okay, again, if you are already confused by the linear algebra stuff, it's okay, don't worry about that. You can go back home and then try to do the math again. You can still follow that. Yeah, so let's say if you believe me, this is the jth basic direction, right? If you want to change one of the non-basic variable to 1, all the others still keep at 0, and this would be the change for the basic variable. Okay, so the question is, let's say if this is a feasible direction, if we move along these direction, how much will the objective change, right? The idea, of course, the idea is you are standing at a solution. Now there are different directions you can search, right? You can search along those directions, but you want to say which one are the good direction you can search for, right? So they are, let's say, they are different directions you can search, right? So you want to evaluate how much will the objective change when you search along the direction you just defined, right? That's a motivation of doing that. And you can calculate that very directly just by taking the C transpose dj, right? So the d superscript j is a jth basic direction. And you can calculate if you move along that jth direction, how much will the objective change? So this thing is called the reduced cost of the jth basic direction or the variable xj, right? Okay. And the formula is Cj, C sub j minus Cb transpose B inverse Aj. That's a very popular formula to remember. We are going to use it again and again. Yeah, okay. That is the reduced cost. Okay, now after defining the reduced cost, we are finally here. So this one is if you are going to remember only one single thing, that will be this theorem here, okay? So if you consider a basic feasible solution X associated with a basis matrix, and the C bar be the corresponding vector of the reduced cost, then this theorem says if all the reduced costs are positive, then X is optimal. But the inverse is not true. The inverse is only true if X is non-degenerate. Okay, so there's a proof for that. Okay. So let's absorb it a little bit. Okay. So first of all, remember how did we define all the basic direction, right? So in defining the basic directions, we are trying to change each of the non-basic variable from 0 to 1, right? So they are n minus m basic directions, right? And the reduced cost means if you are going along those basic directions, how much the objective will change. And the theorem is saying if all the directions, if you are going along all those basic directions, you are going to increase the cost. Okay, that means you are at the optimal solution, right? Because you tried all those directions already, right? And then none of them are going to help you decrease the cost. That kind of certify you are already at the optimal solution. Yes?
Do we not have to check the non-basic directions as well?
Yeah, so that is what the theorem says, right? We don't need to check the non-basic direction. We only need to we only need to check those basic directions and the reduced cost. Okay. I only have 30 minutes now. Took longer than I expect. So maybe if we still have time, we should come back to prove at least part A of this theorem. Or maybe I can just read it very quickly. Okay. So the way to prove that is the following. Let's assume if all the reduced costs are greater than equal to 0, then let's pick an arbitrary feasible solution. We define a direction D, right? The direction D is the difference between the new solution Y and X. And if you use feasibility, that implies both AX and AY has to be equal to B, right? And therefore, this direction has to satisfy AD equal to 0, right? And you can write AD equal to 0 in this form. Similarly, you break it down into the basic part and the non-basic part, okay? And since B is an invertible matrix, right? It's an m by m matrix. You can write dB, just multiply the B inverse here, okay? And now after you have calculated the basic direction, let's calculate how much the cost will change if you go along the direction D, right? So that's what you can do by calculating C transpose D, right? So in this part, if you can still break it down into two parts. The first part is CB transpose DB. So DB is already determined, right? And Jatni, the question you ask is why don't we have to check the basic why don't we define the basic directions, right? The reason is that those are kind of dependent on the non-basic directions already, since B is an invertible matrix. And amazingly, you can check that after you write it this way, this part is nothing but the reduced cost, right? If the reduced cost is non-negative, then it's not worth moving along the non-basic direction. Okay. Yeah. So that kind of proved the theorem. But the inverse is not true. You need a non-degenerate assumption. Okay. You can check the inverse part is also pretty straightforward. Okay. So now we talk about the optimality condition. Then you can claim that a basis matrix is said to be optimal if, first of all, it has to be feasible. Right? The XB has to be greater than or equal to 0, and the reduced cost has to be greater than or equal to 0. Then you can argue that a basis is optimal. Okay. Yeah, so now we are going to talk about the simplex algorithm. I would say this part is not as important as the optimality condition. A lot of people, when they teach linear programming, they spend most of the time on simplex methods. But I would say if you already know the optimality condition, perhaps you can reinvent simplex algorithm yourself. It's nothing but you keep searching along those non-basic directions until you have all the reduced costs to be non-negative, right? That's the idea of the simplex method. Okay, right. So we would like to search along those directions until the reduced cost is non-negative, right? But what if we are not at the optimal solution yet? That means there must exist a reduced cost of the non-basic variable which are negative, right? Otherwise, you already prove optimality. Then if that is the case, we can move along the j's feasible direction, dj, to further decrease the cost, right? So remember the reduced cost is a change in the objective function when you move along the j's basic direction, right? So if the reduced cost is negative, as long as you move along the j's direction, you will get a decrease in your objective. That's the idea of the simplex method. And how far we should move, right? Of course, it is desirable to move as far as possible because you know that when you move along that direction, the cost is always going to be reduced if the reduced cost is negative, right? So the step you should move is a maximum step size such that you are still in this polyhedral P, right? So in other words, you want to maximize the step size such that when you move along this direction D, you are still in this polyhedral set, right? That's just a construction of the simplex method. And the resulting cost change to the objective would be, C transpose D times this theta star you calculated, right? Yeah. Okay, so the questions here? Yeah. Now the next question is how do we calculate this theta star here, right? The theta star is the step size you can move such that you remain in this polyhedral set, right? It's not so trivial to calculate the step size. So in order to calculate the step size, we need to check two things, right? Remember in the standard form, we have two sets of constraints. One is the equality constraints, right? And by construction of the search direction, the equality constraints are already satisfied. Right? Remember when we are constructing the direction, we force the equality to be satisfied. Okay. So in other words, this x plus theta d can only become infeasible if the inequality constraints are violated. In other words, if one of those components become negative, that's when you go out of this polyhedral set, right? Okay. Maybe someone should ask a question. Yes.
So do you have to search along every basic direction for every basic feasible solution?
Oh yeah, you are raising another point which I'm not going to cover. So you just that's a very very essential decision in simplex algorithm. I say there might be many variables where the reduced costs are negative, right? Which one do you pick? Okay, yeah, that's an important decision in simplex method. We are not going to the detail of that. Let's just assume we pick a random one. Okay, right. Usually there are different rules you can choose those variables. Maybe you can just give them a number, pick the first variable first, and then that's called lexicographic pivoting. There are other things like you want to pick the one that gives you the largest decrease in the objective. You can also do that. Okay, so we are not going to talk about those algorithmic details. We are just going to talk about, let's say, the rationale of deriving the simplex method. Okay, so yeah, this is too dense. Let me talk about this very slowly. Other questions here? Okay, so now let's say we are going to move along a direction D. Okay, so when we move along a direction D, there are two cases that can occur. So if all the components of D are greater than or equal to 0, right? So remember, when we are going to check whether moving along this direction violate the constraints, we only need to check the inequality constraints because by construction, we already force the equality constraint to hold, right? So let's check all the inequality constraints. So if all the components of D are greater than 0, and then we are moving along the direction x plus theta D, we need to force them to be greater than or equal to 0, right? And then it is very clear that for any theta greater than or equal to 0, x plus theta D will always be greater than or equal to 0. Why that is the case? Because the original x is non-negative, right? And the vector D is non-negative. And you can move along that direction as much as you wish, right? So that means we can set the theta star to infinity, right? What does that mean? That means the problem is unbounded. Right? You can move along that direction D, always going to decrease the objective, and you never violate the constraint. Right? That is case A. And case B is there has to be one of the vectors Di, one of the components of D such that it is strictly less than 0 for some I. Right? And then the constraint becomes, okay, so let's just consider this component I. We need to keep xi to be greater than or equal to 0, right? So that means the theta has to be less than or equal to minus xi over D, right? That's just a simple way to do it. When Di is strictly less than 0. Okay. And you have to check this for all the Di less than or equal to 0, right? So check this for all the I, that di is strictly less than 0. Okay. As you can imagine, once you check those step size for all the di, you can pick the minimum step, right? Because when you are over the step size for any of the component, you will go outside the polyhedral. So in other words, you should theta star here will be equal to the minimum of index I, such that di is strictly less than or equal to 0. Okay. So if I'm going to interpret that is, if you pick a component I, this is a maximum step you can get for component I, right? And we have to check all the component di less than or equal to 0, and we have to satisfy all those constraints, theta less than or equal to the step size. That's why the maximum step you can get, theta star, would be the minimum over all the components I, right? That's essentially the simplex algorithm, right? Now we have already talked about the two things. First is which direction you should pick, right? You should just pick a direction with negative reduced cost, that you can reduce the cost, right? And the second thing is that once you find the negative reduced cost, how long can you go along that direction, right? So this step kind of tells you this is a maximum step size you can go along that direction. Okay, that's pretty much the simplex algorithm. Then you keep iterating until all the reduced costs are positive. Yes?
So basically, as you move,
Yeah.
do you just keep hitting like vertices?
Yeah, exactly. That's a property we can prove, but we don't have time to prove. So you will keep hitting vertices. Okay.
Okay, so you basically like bounce from one vertex to another.
Yeah, exactly. Yeah, so to say why this is a case, we can check what's happening here, right? So remember the basic direction is that you make one of the non-basic variable to be positive, right? All the original non-basic variable are 0. Now you make one of them to be positive. On the other hand, one of the basic variable will become 0 because you are picking one of those indices among the basic variables. And if you are picking let's say, this index L achieves the minimum here, right? You are hitting the boundary using index L. And when you are hitting the boundary, that means this variable with index L will go to 0, right? So remember, when we are deriving this constraint, that is a non-negative constraint we are trying to derive. And then the step size we derive is to say we want to keep satisfying those non-negative constraints. And when you are picking the maximum step, there will exist one of these variable L such that this variable will become 0 when we search along that direction, okay? So which suggests that this variable J we pick, J is a variable with a negative reduced cost. And it will replace a basic variable in the basis. Okay, so usually when in simplex algorithm, people just say this index L leaves the basis and J enters the basis. Now you can show that after this step, you are going to arrive at a new basic feasible solution. Okay, so each iteration you will stay at a basic feasible solution, and you keep iterating until all the reduced costs are non-negative. Then you are done. That's pretty much a simplex algorithm. Okay. Yeah, so that's almost everything I want to cover. The next part is some very tedious calculation of the simplex algorithm. We can show you an example how this can be done. Okay. But before that, let's make sure we are all good. Okay. Yes.
From the size of the initial matrix A.
Yeah.
and do we know how many vertex in the worst scenario we had to check every single vertex?
Yeah, so that's a good point. So that's like the computational complexity of the simplex algorithm, right? In the worst case, it can go exponential. Okay, so even though linear programming is polynomially solvable, but if you use a vanilla simplex algorithm, you can get exponential complexity. Okay, so there are people who work on polynomial time simplex methods, right? That would be some modification to the original simplex method. But even though that's exponential complexity in the worst case, usually in practice, simplex method works pretty fast. Does that answer? Okay. Yeah. So that's just a summary of the simplex method. In summary, you just pick a reduced cost that is negative, then search along that direction to see how far you can go. And then you can get the optimal theta star using this formula here. Then once you do that, one of the basic variable will leave the basis, and another non-basic variable will enter the basis. Okay. Yeah, so the next part we will cover very quickly. Although it is quite complicated, is how do we compute matrix inverse faster? Okay, so remember that at each step of the basic of the simplex algorithm, you need to compute the matrix inverse for the basis matrix, right? And that is expensive because computing a matrix inverse takes m cubed computational complexity, right? So in practice, people don't want to take matrix inverse at every iteration. And there is a trick that can be applied to avoid that. Then you only need m squared computational complexity. And that's from a very simple observation. Remember that originally, the basis matrix, it looks like this, right? You pick m of those basic variables, right? And in the next iteration, let's say this is a new basis matrix. These two matrices are very similar, right? Because you only change one column of this matrix. One of the variable leave the basis, another variable enter the basis, right? So you just replace the lth columns with the jth column of this matrix. You only change one column of this matrix, okay? Then we can exploit this information of B inverse to calculate this B over line inverse. Okay, so the rest is a review of your linear algebra class, okay? So if you consider B inverse times the basis in the next iteration, you realize this matrix has a very good looking structure, right? It's almost an identity matrix, except this column you just changed, right? Because all the columns are the same except the lth column you just changed. Then you can do some elementary row operations to change this matrix to an identity matrix, right? So the way is that realize that this is the only column that is not a unit vector, right? Then you can use this element to eliminate all those entries, okay? And eliminate all those entries, and then finally you divide both sides by U sub L. Then you will arrive at an identity matrix, okay? If you do this operation, that only takes, I think if you do those row operations, that takes m squared computational complexity, okay? Yeah. And in practice, the way people implement simplex algorithm is called the full tableau implementation. I'm not going to the details of this part because this part is not required, but it will be more efficient to implement it this way. So the idea is, since this B inverse and the next iteration are very similar, right? Then you only need to consider those row operations. Those row operations to make it a unit, identity matrix, okay? Yeah. So if you look at this part here, let's assume all the row operations be Q. Then if you multiply by Q, this will be the identity matrix. And then if you would like to calculate the new inverse efficiently, you only need to multiply Q to the inverse of B. That's a trick we can apply. Okay. Yeah. And similarly, if we want to update this so-called simplex tableau, initially remember we have the original basis inverse times the A matrix. Now we are changing this matrix to B bar. We don't really need to compute this inverse all over again. We just need to multiply this by Q. Q are the unit elementary row operations. Okay. And in practice, when people implement this, they not only consider the constraints, but they consider the objective as well. This is like the reduced cost. You keep them in the tableau as well. And you can show that in order to update the rows and columns, you just need to do these row operations, and then you also should do the row operations on the objective to recalculate the reduced cost. Okay, so this part is very tedious to prove. You just assume, let's just assume it is true. Otherwise, I need 2 more lectures to prove this part. That's why I say this is not required. You only need to know the vanilla simplex method. You can calculate the matrix inverse from scratch. That's fine, right? But here's I'm just telling you how it is implemented in practice. I'm not going to do it in detail. Let's just look at an example. You will quickly know what I mean here. So let's say you have a very trivial example here with some variables. Then in order to apply simplex methods, you should add slack variables, right? Let's say there are some inequality constraints. We add some slack variables. Okay. And then after adding the slack variables, we can observe that there is a very trivial solution we can start with, right? We just pick the slack variables to be the basis variables, right? Just set x4 equals to 20, x5 equals to 20, x6 equals to 20, and all the rest equal to 0. Then we can start with a basic feasible solution. Now we can start the simplex method, okay? So to start with, let's say you calculate the B inverse, and you get that x4, x5, and x6 equals to 20. And those columns are, so this part of the columns, they are the B inverse times the matrix A. Okay, so for each column, you just calculate B inverse times the column vector, right? And then in this part, okay, so this part is the reduced cost. Okay. And now we find that one of the reduced cost is negative, right? And then that means we can search along that direction. And how far we can search, we can divide, we can search the step size. That will be, you take the current value divided by this U vector here, right? So we just divide this entry by this entry, then you got, for each of these variables, 20, 10, and 10, okay? And that means you can only search it for 10 step size, right? You are picking the minimum vector. Then we determine this part, this entry can be the pivoting row. The next step is to do the row operations. We want to eliminate those entries such that this column will be a unit vector. Okay, that's the row operations. Okay, maybe you are not connecting the dots, but here I'm showing the operations. You can use those operations to make this. Okay, so now you have this column here. Then the next iteration, this column will become a unit vector by doing the row operations. Okay, And then you can continue to do the same thing. We find another column with negative reduced cost. Then we do this again. Eventually, you will find out that you arrive at a solution with non-negative reduced cost for all the variables. Then we can claim it is the optimal solution. Okay, so that's how people implement that in practice. There will be a homework question related to Simplex algorithm. You don't have to follow this Tableau method, but if you wish to read it, that's also fine. We can just implement the vanilla Simplex algorithm by hand. Or if you want to practice your coding skills, you can develop a Simplex solver in Python to solve any arbitrary linear programming problem. Okay. That's all I have. So this is chapter 3 of our reference book. Okay. Any final questions? Yes.
So how do we know that the basis matrix remains non-singular after like every transversal?
Wait, did you read the book or no?
No, I'm just coming up with these questions.
Okay, you have a good talent for doing mathematics. That's a theorem you have to prove. Yeah, that's a. So you can prove that after you do this pivoting step, you have to prove that B matrix is still invertible, right? The proof is not very straightforward. That's why we didn't cover that.
Okay, but it's true.
Yeah, but it's true. Yeah. Otherwise, you have a problem. Yeah.
Yeah.
Okay. Other questions? Okay. Yeah. Thank you.